Today, we're going to learn section 4. I call it known distributions. In this section, we will study several very important discrete random variables that we will apply to model the claim frequency. That being said, this section is by far the most important one. And I would argue it's possibly the most important section of this chapter. So please pay a special attention to the content of this section. So here we go. Let's start with the first one. The first one is a Bernoulli distribution. A random variable x has a Bernoulli distribution if the definition of it is given by the formula below. So this is how we define a Bernoulli distribution. Basically, we can call it a 0-1 distribution, meaning x can only take two values, either 0 or 1. Probability theta is the probability that x equals 1. And obviously 1 minus theta is the probability that x equals 0. So here our convention is to assign theta to the value of 1. Of course, you can switch to 0 if you want. Here to make things more consistent, let's do our best to try to stick to the same definition. Okay. So in what applications you may apply Bernoulli? An easy application would be a coin example. Okay. Let's say we consider head to be 1. We consider tail to be 0. So if you toss a coin, if head shows up, you get $1. If tail shows up, you get $0. So that's a Bernoulli distribution, right? And if this coin is a fair coin, then theta is 50%, right? But of course, this coin can be a biased coin, like it favors more of tails, then we can set theta to be, let's say, 20%, strictly less than 50%. In general, Bernoulli distribution applies when we have two disjoint categories, which we can call success and failure. You can think success as for the value 1, failure as for the value 0, which means if you run some experiment and in the end, if you get success, you assign value 1. If you get failure, you assign value 0. So it's rather general, right? For instance, if you want to discuss, let's say whether you pass this course, right? So you can think passing as success, right? And then theta will be the probability that you pass this course. Okay. So it's basically when you of course here for success and failure, it's more of on the notional side, right? So it does not have to be exactly success, but in the coin example, you can think head as success, or you can think tail as success. So it's more of a personal choice. So in general, anything that has two separate results, okay, you can somehow apply Bernoulli distribution, right? All you need to do is to assign value 0 and 1 correspondingly to the success event and to the failure event, okay? So given the above definition, the next result of expectation and variance should be very straightforward, right? So in this case, the expected value, well, is the value which is 1 times the probability plus the value which is 0 times the probability 1 minus theta. So obviously the expectation is theta. Variance, I can directly apply the definition. So value minus the mean squared times the probability plus value minus mean squared times the probability, right? Okay, let me keep writing. Obviously, theta times 1 minus theta is the common factor of these two terms. So once I worked out this factor, the first term will be left with 1 plus theta. The second term will be left with theta. So together I get 1. So that's why I have theta 1 minus theta. Okay. Those results are, they are very easy to derive, but they are somehow important. Later on, we will see how we can use this to figure out the expectation and the variance of a binomial distribution. Bernoulli distribution is about one trial. Okay, when you have one trial, you can talk about success and failure. Again, we can use the coin example, right? We can talk about head and tail, but if we toss a coin more than once, let's say we toss a coin n times, right? What we get is a sequence, right? It's not just the one success or one failure. It's a sequence of success or failure events. Okay. In this case, how do we study the number of success? Right. In the Bernoulli example, it's either 0 or 1. Now we have many choices. So let's say we repeat a Bernoulli trial n times. Okay, and we use xi to denote the result of the ith trial. Again, we assign value 1 when we get a success event. When we get a failure event, we're going to put value 0 for xi. So xi is either 0 or 1. That means each xi is a Bernoulli random variable. Okay. Now, after repeating the same trial n times, and here we assume they are independent. This is likely the case when you use the coin example, because when you toss a coin, the result of the previous one has nothing to do with the following ones, right? It's memoryless, right? It has no memory on the previous one, so it's reasonable to assume they are independent. In this case, we have an independent of n repeated Bernoulli trials. Okay, so which means they are the IID, independent and identical distributions. And what we want to know, we want to know the total number of success events among those n trials. Okay, not any particular one. We want to know the total of all trials. Okay, so obviously what we are trying to do is sum up, right? We are trying to sum up the results of all trials. That means what I'm interested in is x1 plus x2 all the way to xn. Okay. Since each xi will be either 0 or 1, so my x, the smallest possibility is 0, which means all of them are 0. Let's say I toss a coin n times, and every time I get a tail. So then it's I have n failure events. Okay, obviously goes all the way to n. Okay, small n is the maximum value I can possibly get, meaning for each tossing I get a head. Right, so that's the luckiest case I can possibly hope for. So now the question is, now this is the sample space, right? Okay, the next question is to assign probability for each one, right? So what we want to know is what is the probability that x say equals 3? Okay, so we want to know that. Okay, I claim that this is a Bernoulli distribution. In this scenario, I know the probability function is given by this particular form, and let's just study. Okay, here I want the number of success to be x times. Okay, obviously this x will be between 0 and n, between 0 and n, which we already discussed. Now we are discussing about why this is the probability function. Okay, so the way I interpret is I draw different boxes. Okay, I have n trials, so I'm going to have n boxes. Okay, in each box I will need to fill the result, which is either a success or a failure. Right now I need how many success? I need x. So let's say x is this x. Okay, so I need somehow x of them, which means for the remaining they are failure. Okay, how many? We have n minus x. Okay, so this is only one possible scenario. One possible. Okay, in this possible scenario, the first x trials are success, the next n minus x trials are failure. Okay, for this very specific scenario, I know the probability is theta to the power of x, which characterizes the first x results, because in order for a trial to be a successful event, the probability is theta, right? That's given from the Bernoulli distribution, okay? And here I have x of them. Because they are independent, I'm multiplying them together, right? So that's why I have x, I have theta times theta all the way, x of them. So that's why I raise the power to x. For the same reason, I have n minus x failure events. I do the same thing. The probability of a failure event is 1 minus theta. There are n minus x failure events. So I raise the power to n minus x. So this is the probability for one possible scenario. So the next question is, how many scenarios do I have for x success events? I say this is select x out of n. So that's a combination number, okay? And the order doesn't matter because we don't care the in which child you get success. All we care about is the total number. So so in this case is C instead of A because it's not permutation, right? So we only want the standard combination, and that is sometimes we write selecting x from n possibilities, right? So the result is here. So this is the actual calculation formula for the combination number. That is the mathematical analysis. Nevertheless, for the textbook, they just give this as a definition, meaning in the textbook, a binomial random variable is defined as this way. So let's say if x is a binomial random variable, then the probability function of x is defined in this formula, okay? So they treat this as a definition, but I just gave you the mathematical deduction, behind this formula, okay? The notation is here. En stands for binomial, okay, binomial distribution. And the first parameter is the total number of trials. So n is the, let me write it here, binomial distribution n theta. So here n is the total number of trials. Okay, and the theta is the probability of success event in a trial. Of course, for all the trials are identical and independent. So, they have the same distribution. So next, let's study the properties of a binomial distribution. First, I ask you to check this, okay? Basically, what I want you to do is to study, let's do the general case, not this. What is, let me use A and B. What is this? How do I open up? Of course, if n is 2, you know how to open, right? So let's say a special case, a plus b squared is a squared plus 2ab plus b squared, right? A plus b cubic is a cubic plus 3a squared b plus 3ab squared plus b cubic. Goes on. How do I know the expansion is exactly what I just wrote down? That's when I need to apply the binomial expansion, right? So a plus b to the n will be, okay, cn0 is an. So the meaning is, here I'm talking about picking b, right? So in order for this to give me the term of a to the power of n, I cannot pick any b, right? Because this is essentially a plus b times a plus b, n of them, right? And in order to get a to the power of n, each of them must be contribute a. That means none of them contributes B. That's why I have Cn 0. Okay. The next one is An minus 1B. So obviously here I need 1B. The rest is A. So here I need to choose one out of n, right? There are n choices, right? I only need one and one of them, okay? Which can be from each. I have n choice, so it's one from n goes. The next one, obviously, I'm picking 2 because now I need the b squared, right? And it goes on all the way to cnn, which is b to the power of n. So that is the so-called binomial expansion, right? So once you have this formula, you can easily check why it is 1. Because a is theta, b is 1 minus theta, right? So inside is 1. 1 to any power is 1. So that's why this is 1. Okay, next I want to show the expectation is n times theta. There are many ways, okay? The one possible way is to really do the calculation, right? So let me give you, I need additional page. So let me get a page from here. Let me get a page to write with more details. Okay, so I want to show this is n theta. So of course, right now, our x is a binomial distribution with parameters n and theta. N is a positive integer, theta is something between 0 and 1. Okay, we know by my mathematical arguments, that is, right? So each xi is a Bernoulli distribution. Let's denote as BE theta, right? And because expectations are linear operators, right? And we know for each one, they are the same, and the expectation is theta. So I have summation, n summation, of theta. So it's n theta. This is likely the easiest way of proving the expectation result. Of course, by the same reasoning, I can do variance as well. Because they are independent, right? All the xi's are independent. Because they are independent, the variance of the summation becomes the summation of variance. Okay, and obviously I already know for each one, the variance is theta times 1 minus theta. That is the result from the Bernoulli distribution as well. So again, I easily prove the variance is n times theta times 1 minus theta, right? So if you truly understand my construction of binomial distribution, I don't think you really need to memorize, right? So it's rather straightforward to understand those two results. And if we treat definition 17 as the definition for binomial distribution, to prove those two results, it's slightly more challenging, but not impossible. What I mean is, okay, so this is the first method. I can try a different one, for instance. Okay, so this is the, let's call it the stupid way. It's also the more direct method of showing it. Okay, so it's x times the probability, right? So now let's copy the probability. So it's n factorial, x factorial, n minus x factorial times theta to the power of x, 1 minus theta to the power of n minus x. Okay, so obviously, let me get a different color to do the notation. So obviously, I can add this to cancel here, right? So it becomes x minus 1 factorial. Okay, so I do one more technique change down here is So now I have n minus 1. So here the starting point of is 0. Okay, so 0 doesn't matter because if n is 0, I can let me put it's not n. Here is let me erase this. I'm using x, so the starting point is actually x. Okay, and obviously the 0 case I can ignore. I can simply start with 1. When x is 0, 0 times anything is still 0. So I have this, right? So when we add this up, it's actually n minus 1. So that motivates me to take out the n and leave inside as n minus 1. Okay, which means I'm trying to change the total number of trials from n to n minus 1. That is something I'm trying to do. Okay, so now what I have is n times n minus 1 factorial. Here is x minus 1 factorial, n minus x factorial. Okay, so I want to match those two, right? Remember, it used to be x, they match each other. Here's n minus x, here's n minus x. Now I have x minus 1. So I'm going to break this as x minus 1, leave the x outside, leave the theta outside. Okay, so I don't change anything. 1 minus theta n minus x. Okay, because this is a constant, it has nothing to do with x. So let's factor out. Okay, now let's introduce, let's try what do you want? You want, let's say, y equals x minus 1. So y from 0 to infinity, n minus 1 factorial. Here, x minus 1 becomes y. Okay, n minus x will be n minus 1 minus y. Okay, factorial. So here is theta to the power of y. Here's 1 minus theta to the power of n minus 1 minus y. Okay, so you think n minus 1 as the new n. So if you're still not convinced, let's use n ply to denote n minus 1. Okay, so then what I have this to be n ply factorial. Here is n ply minus y. So if you compare, this is the summation of another random variable. Here, if I denote y is another binomial random variable with parameters n minus 1 and the same theta. So of course, when I sum up over all possibilities, what I get 1, right? That's already the result we just proved here. So if you have any random variable, sum up over the entire possibilities, you get 1. Oh, by the way, I made a huge mistake. That is here. Does not go to infinity, right? But that is okay. Here, go to n. The next one go to here it's still n, but here is n minus 1. Okay, that's because it should fit with the first parameter. So again, this is 1, so this is n theta, right? For the same reason, you can apply the same technique to work with, okay, this is slightly more complicated. I leave this as extra homework. So you can try to work on the second moment. From the second moment, you can get the variance, okay? So I provide a second method to show the expectation and the variance result, okay? So let's go back to the slides. The next result is about the moment generating function. You need to know the definition. Let me go back to the regular color I use. Let me go to the color I use. Okay, so for the moment generating function, you should know this is the definition. Okay, I ask this question to you. Are you able to prove this result This is actually easier than the one I just showed, because now what you have is in the exponential term, right? Let's try. Let me go to the next page. Here we have more space. So now we want to show MGF. Okay, mx at t. So this is a function of t. I take expectation for the exponential of tx. So let's do it from 0 to n. Okay, e to so here it becomes small x because I consider all the values. Here is the random variable, so it's the capital X. So here I don't need to do anything with the combination number, so I keep it. So I mentioned this is easy to do because all you need is to collect them together, meaning collect like terms. What I have, it's theta times e to the power of t. Okay, then it's x. 1 minus theta m minus x. Okay, then recall our general binomial expansion. Well, is it? The binomial expansion is here, right? So you have a different a. B is still the same. B is still 1 minus theta, but a is no longer theta. A will be, according to this is your a, right? So this part is your a. This part is your b in the binomial expansion. So my result will be theta times e of t plus 1 minus theta to n, right? Because the maximum is n. So this is exactly what we have down here, right? So I just proved the MGF. Well, after proving MGF is trivial, right? All you need to do is to take log t for t. So once you take log t, e of log t is t. So that's why. Okay. So I replace this by t. So that's what I have for the MGF. By the way, once we have MGF, we can also apply the results. Remember, let me go back a few slides. Let me show you that important results. Where is the result? I think it's in the MGF, the definition of MGF here. So once you know MGF, you can differentiate, right? If you want to know the first moment, you differentiate once. If you want to know the second moment, differentiate twice, and always evaluate at 0, okay? And if you want to know the corresponding probability function, you can differentiate the probability generating function. But remember to divide by the factorial, okay? Now let's go back to the formula here. Okay, let me differentiate once. Okay, you need to differentiate at general t first. Okay, after you obtain the first derivative, you then plug in 0 for t. You do not plug in 0 earlier on, okay, in the function. So now what do we have? First of all, this is in you need to apply chain rule, right? So you have a power function in the outside. So power term goes down. The original power will be reduced by 1. Okay, so that's the derivative of the outside function. Then we do inside. Again, this function is a function of t. So 1 minus theta, or theta is constant. So constant stays. Exponential, when I differentiate, is the same. Then plus constant that gives me 0, okay? So I know my expectation will be the first derivative of my moment generating function at 0. So I plug 0 for t, e to 0 is 1. So I have theta plus 1 minus theta to n minus 1, theta e to 0 is 1. So it's n times theta. So again, this is method 3 to prove it. Well, there are just so many methods to get to this result. By the way, we also have the result for the moment for the probability generating function. So check this is correct. Okay, it shouldn't be that complicated. So next, given the probability function, we can easily work out sometimes we call this the recursive, right? Because it gives you a connection between the probability at x and the previous level, x minus 1. So if you know the probability at 0, you can apply this recursive formula many, many times to get to the probabilities for all possible results, right? So this is a nice recursive formula. In the end, in the next section, we will sum up them. So this should be straightforward, right? All you need to do is to do a little bit manipulation on the combination number, okay? So if theta is 1/2, in this case, it's a symmetric, right? Symmetric means you have 50-50 chance of seeing a success event or seeing a failure event. So it's equally likely. If theta is more than 1/2, it's negatively skewed, or you can call it skewed to the left. So, but that's not entirely important. Okay. The last one, it's quite hopeful in some applications, because for insurance company, the number of policies is huge. So you can apply. So let's say if you apply binomial distribution to model the claim frequency for one policy, and roughly assume the policies are independent, then by the standard theory, you assume each policy is a Bernoulli, and then when you add them up, you get a binomial distribution with a huge n, right? N is huge. According to the last point, when n is huge, you can approximately assume this is a normal distribution. And for normal distribution, you have very, very nice table, okay? So that's very hopeful. I give you this kind of like a graph to show the case when you have different thetas. Okay, so for example, the first one, theta is 0.1, 0.3, 0.5, 0.7. Obviously, this is symmetrical, right? You can easily see this is symmetrical graph. And when theta gets bigger, it has more weight on the left-hand side. So if I roughly draw this graph, it's skewed to the left, right? So the left-hand side has more tails. So it's called the negative skewed or skewed to the left, okay? I will stop here for this video. In the next video, we will continue our studies on discrete random variables.